All right, so this video is going to be on substituted cycloalkanes. So what does that mean? Basically, it's when we have a substituent on a cycloalkane. And so we would replace a hydrogen with something else. Okay, and so a very basic example would be like this. So we basically replaced one of those hydrogens with a methyl group, right? And so this is now a substituted cycloalkane. More specifically, it is a mono-substituted cycloalkane. Okay, so mono meaning one, and it only has one substituent, and so that is what this methyl cyclohexane is. And so we can draw this in the chair conformation, just as we did before. So draw our parallel lines, draw a nice little angle there, and there's one chair conformation, right? And so where do you want to put the methyl? I personally like to put all my stuff over here if I can, and I'll go ahead and draw this hydrogen. Well, we might as well just draw all of them. Okay. All right, so we've got our one of the chair conformations for methyl cyclohexane. Okay, and so this can actually undergo a ring flip as we saw before, and this is an equilibrium process. Let's not worry about drawing the boat conformation, but just focusing on, whoop, I totally just drew the same chair. And there we go. Those ones are crazy for me. Let me draw that better. There we go. And so now, if we're focusing on where that methyl was, it was on this carbon, which is now this carbon. So as we stated before, the up C's become the down C's, right? But also, remember what we stated was that if you have a hydrogen, for example, that's on a down C, this guy right here, we've got this hydrogen, it's axial down, okay, is what we would refer to that as. And notice that carbon is up, right? But that hydrogen is now equatorial, cool. That's fine, but the main thing that I want you to remember is that axial down hydrogen here is now an equatorial down hydrogen. Okay, so it was a down hydrogen there, and it's a down hydrogen here. Okay, so the reason why I mentioned that is because what we have is not an up hydrogen, but an up methyl group. And I want to point out that we need to have that methyl group pointed up here as well. Okay, and so that means we're going to have the hydrogen elsewhere, or down axial, as it was down equatorial on the other structure. Okay, so this is important again for when we talk about whether or not things are cis or trans, which we'll do shortly. And I'm not going to draw the rest of the hydrogens. I think that's fine. We can just draw axial and hydrogens, axial and equatorial. But what we do want to point out is that one of these is more stable than the other. Okay, and what do you think it is? Which one do you think would be more stable based off of the structure of these two? We have, what's the difference? They're all hydrogens except for the methyl group. So this methyl is axial, and this methyl on this particular chair conformation is equatorial. So if you said that this one was on the right was more stable, then you are correct, because if you have a substituent, then we want that substituent at the equatorial position. Okay, more stable substituent is at the equatorial position. Okay, I'm abbreviating a lot of stuff, so hopefully you're keeping up with the audio as well as what I'm writing. But the reason why we want the substituent at the equatorial position is because of something called 1,3 diaxial strain. Like, dang, there's like all kinds of strain, right? It's pretty much just like a steric strain, if you want to think of it that way. But it's very specific in that this, let's just call this the 1 position. So that's the 1 position. And then we would have this the 2 position, and then that would be the 3 position, right? And so if we're saying 1,3 diaxial strain, that means that we are referring to the axial substituents. In this case, they are both hydrogen, but they are projected upward, basically interacting with the methyl group that is on the axial position on the first carbon. And so this is going to cause something, this is referred to as 1,3 diaxial strain, and is basically going to result in steric hindrance or steric strain. And again, this is why we want our substituent to be at the equatorial position, because we can actually draw our equilibrium with the larger arrow headed to the right and then a little baby arrow headed to the left. And that means that we are favoring, in our equilibrium, we are favoring the structure on the right, and we favor it in a 95% to 5% manner. So there, basically, if we took a look, let's say we took a picture of 100 molecules of methyl cyclohexane, 95 of them would be in this equatorial, would have the methyl in the equatorial position, and only 5 of them would have it in the axial position. Okay, and that's just basically a testament to the effect that 1,3 diaxial strain actually has. Okay, and the destabilization associated with that's going to be about 3.8 kilojoules per mole for each of those HCH interactions. Say, so HCH3, interaction. They cost 3.8 kilojoules per mole. Okay, and since we have 2 of them, that means that we have a structure that's 7.6 kilojoules per mole less stable. And that's interesting, right? Because 7.6 kilojoules per mole doesn't seem like that much, but apparently it is, because we have a 95 to 5 ratio for the presence of each of those particular conformations. Okay. All right, so let's take a look at another example. Where we have something that's bigger than a methyl group, and then we'll kind of see what we think we might observe in terms of the equilibrium and the population of each species. So let's say we've got this cyclohexane with this group on it. Do you guys remember what the chicken foot group is called? That is a T-butyl. So if you said tert-butyl, then you are a winner. Winner, winner, chicken foot dinner. Ha, didn't even plan that. I hope you guys get a hoot out. They get a laugh out of my my weird, silly jokes. But if not, I do. So it's cool. Let's take a look. We've got one chair structure here. Let's do a little equilibrium arrow. That'll give us the opportunity to draw the other chair structure. Now, here's where I would ask you, where do you want to put your tert-butyl? And I told you I like to put it here. Do we want to put it axial? Do we want to put it equatorial? Let's just do this axial because it looks so pretty. And when it's like that, just sitting on the top of that. And then what we've got is, after that chair flip, remember, this particular tert butyl group is pointed upward, and so it's going to be upward on the structure on the right, but it's going to be in the equatorial position now. Okay, and so let me ask you, which do you think is more stable, the structure on the left or the structure on the right? Ding, 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 ding. I'm assuming you got it right because you're awesome and you've paid attention. But this one right here is more stable, right? Because remember, we want the large substituent, or just substituent in general, on equatorial position. The equatorial position. All right, so it turns out, well, let me ask you the next question. Do you think that since it is more stable, that means that there's a higher population of this species, right? As opposed to this one right here. So what do you think the percentage might be? If a itty-bitty methyl group is a 95:5 ratio, then what do you think this is? Yeah, I don't know if you got that right, because it's kind of a trick question, because it's actually 100% the structure on the right. That's because this 1,3 diaxial strain is so high in energy that we just don't form any of it. It will not allow a chair flip to occur, and that's why we have 100% of the chair conformation on the right. So the axial, another way to say that is the axial tert butyl is just too sterically hindered. Sterically, I don't know why that seems weird. Sterically hindered, and therefore it doesn't happen. So remember, just make sure your large groups are in the equatorial position. If you have two groups that are like moderately sized, somewhere in between that tert butyl and the methyl, then you can have some percentage of that group in the axial position. But as you can see, when it gets too large, we will not have any. And so this is something that you should remember, because there's some really fun questions related to this. And so yeah, that's pretty much it. Okay, so let's move on to the di-substituted alkanes. So di-substituted alkanes. Now remember, we just basically went over mono-substituted alkanes, and that was when you had one substituent. Di-substituted literally just means that you have two substituents, right? So for example, let's just say we added a methyl to either side of that cyclohexane ring. Okay, so what this does, this allows us to kind of introduce some additional concepts, something called Cis and Trans. Okay, so first let me draw you an example of a Cis and Trans in this particular format. So we can draw a wedge and a wedge, or we could draw a wedge and a dash. Okay, or I mean, technically we could draw a wedge and a wedge, but these guys are actually the same. You just need to flip one of them over and it would be basically the other one. And so it is important for us to remember that the wedge is basically it's pointed out at us, so this is like in front, and then the dash is pointed away from us, and that is basically the pointing to the back. Okay, so this one has a combination of both, right? And so that leads us to another term, or two terms actually. So this one right here, where they're both different, This particular disubstituted cycloalkane or cyclohexane is a trans isomer. Okay, and then these ones right here, since they're both on the same side, these are called Cis Isomers. Okay, and again, this means opposite side or across. I think across might make a little bit more sense to you because like a transcontinental is basically across, let's see, transverse, for example, another word. Basically, that word just means kind of like across or maybe even opposite. So, and cis isomers are when you have something on the same side. Okay. Now, these particular vocabulary words are basically a class of compounds that we're going to call stereoisomers. Stereoisomers. Okay. Now, what does this mean? This is basically the three-dimensional orientation of a molecule is different, but you have the same bond connectivity. So 3D orientation is different, but same bond connectivity. Same bond connectivity. Okay, and so as you can see, this particular structure right here does represent all three of these wedge and dash molecules that I've drawn, but with the wedges and the dashes, we're getting more specific, and we are actually kind of making a note that the three-dimensional aspect of these is different. And so because they can either be both pointing up or both pointing down, or they could be going up and down. And so that's stereoisomers. Stereoisomers, although I find extremely fun, they can be particularly difficult for people to visualize because, I mean, we're writing down organic chemistry on a two-dimensional plane, but trying to visualize it in 3 dimensions. So this is going to take some practice, and again, I encourage you to utilize the molecular modeling kit or some JMOL simulations online. Let's see, let's say we've got this guy, and then this guy, and then we've also got this guy, and sorry, my wedges are like, they're gorgeous, right? I'm sorry, you think you get the idea. I'm sorry, my dashes. So, one thing we want to mention real quick is that the trans and cis, those are prefixes, and those are, when we're naming these compounds, what we're going to do is place them at the beginning. So trans, for example, and then 1 for dimethyl cyclohexane. Cyclohexane. So let me go ahead and steal this guy, bring him back down here so we can actually give the name. And since these two groups are on the same side of the ring, they are cis. And again, we put that in the front. So that's a cis 1,4. I'm going to just copy this. Woo. Boom. All right, so it would probably help if I finished spelling the word hexane. All right, so that's cis and trans 1,4-dimethyl cyclohexane. Now, one of the things that we want to go over is basically the chair conformations of these two. We want to see maybe which one is more stable. So which one's going to be high energy, which one's going to be low energy, if that's even possible. So let's start by drawing a chair. Okay, so here's one chair, and then we will go back and forth, and oh, sorry, I'm so not good at drawing the opposite chair. I've gotten by because I just tend to avoid it. So let's see, we have two methyl groups on. Let's do the trans one first. Okay, so this is trans, and again, this is important, or it's important to review the axial and equatorial hydrogens or substituents and the effect that a chair flip has on it, because remember, once an up hydrogen, always an up hydrogen. It's just a matter of whether or not it's equatorial or axial, right? And so that's going to be the same thing for a cis or trans substituent. Now, so how does this wedge translate into the chair conformation, right? Or how does that dash translate into the chair conformation? Well, let's see. I'll just go ahead and draw these substituents in red. That way we can better understand it. So again, I always like to just start here. So we can actually choose to put our methyl either axial or equatorial. I feel the need to just put it axial, just because I tend to like to put those substituents up in the axial position when they're on that carbon. That's more aesthetics than anything. And so since this particular methyl substituent, which I'm just leaving as a line because it's a skeletal structure, since it is in one direction up here, and then our other methyl group is in the opposite direction, meaning it is trans to it, that means if this is up, then this needs to be down. Okay, so that means if we have an axial up, then we need 1, 2, 3, 4 carbons away. 1, 2, 3, 4 carbons away, we need to have our methyl in the down position. And so at this particular carbon, since it is a down C, the down substituent on it is actually in the axial position as well. So when we do a chair flip on this trans 1,4-dimethyl cyclohexane, then we are a frozen iPad. So hold on, there we go. Got to give myself a little bit more room. What we're looking at now is this is the 1 position and this is the 4 position. Okay, let me get that undone. So 1, 2, 3. I'll put the 4 in there. So these are still at the 1 position. That methyl is still up as I've drawn here, but it's now in the equatorial position, and at the 4 position the methyl is still down. It's just in the equatorial position as well. So let me ask you, maybe it'll be easier to visualize if we actually drew our CH3s in this one. Let's be more explicit. Which conformation do you think is more stable? And if you said the structure on the left, then you should try again, flip the coin again. Maybe you'll get the one on the right, because it is a 50-50 chance. And yes, this one is more stable because we have our substituents in the equatorial position. Okay, substituent in the equatorial position. Okay, so yes, that's going to be the case here, and that means that we can actually draw a big portion of that equilibrium arrow to the right and then a small one to the left. Okay, so let's take a look at the Cis conformation and see how that looks. Okay, nope, we're just gonna do this. So boom, 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 boom. There's one. Okay, now we gotta draw it opposite on this side. Cool. So already getting better. I like it, right? Practice makes perfect, y'all. It's not like riding a bike, but maybe it is. Let's label that 1, 2, 3, 4. 1, 2, 3, 4. Okay, so again, we can pretty much put that methyl group wherever we want. So let's go ahead and draw that methyl in on the axial position. And since this is the 1, 2, 3, 4, sorry, I'm probably confusing you with the way I'm numbering these. Let's do it 1, 2, 3, 4. It doesn't matter. It's the same result because they're both the same substituent. But that means we need to put our methyl groups on the same side. So if this one is up, then the other one needs to be up. So actually, let me change that. Then let me get a little uncomfortable because I want to put this in the equatorial position now, because that puts it in the downward position. So since this is down, then that means we need our methyl group on the 4 position to be down, and since it is a down C, it needs to be in the axial position. Okay, so notice they are both down, but one is equatorial and one is axial. Okay, so what is that going to look like after the chair flip? Well, let's take a look at number 1. That is a down C, and it is a down methyl on the left, so it needs to remain down. So now that's axial. And the 4 position, we have a down C, I'm sorry, this is now an up C, and we have a downward facing substituent, so it needs to be equatorial now. Okay, cool. So now we have an equatorial and an axial methyl group. So which one do you think is more stable? I'll give you a little extra time to think about this one. Alright, if you want, you can pause the video, but I'm gonna move on. And this is also kind of a trick question, kind of like that terp-butyl one, because they are the same. Same stability. Hold up, Jazz. What are you talking about? Are you sure? Well, yes, because as we stated over here, we have one in the equatorial position and one in the axial position. This is in the equatorial position, and this is in the axial position. These are, remember, the axial position creates that 1,3 diaxial strain, and both of the structures have a methyl group in that position, no matter which chair conformation you choose, and so therefore they both have the same energies, because the other one is in the equatorial position. Okay, so this would actually be a 50% population of this, and then a 50% population of this guy. All right, let's see if that's the case for a different type of di-substituted cyclohexane. So since we are on the dimethyl cyclohexane game, let's take a look at not the 1,4, but how about the 1,3? And we'll make, so this one is the cis, and we will do another one that is, I don't know why I'm coloring these in. I always tell you guys I don't do that, and I think I'm just filling in for fun. Okay, so we got a trans isomer here, and then we've got a cis isomer here. The numbers associated with it are a 1,3 now, so this is a 1,3 cis or trans 1,3 dimethyl cyclohexane. So 1,3 dimethyl cyclohexane. All right, so let's take a look at the cis one, just because that's on the left, and we'll go ahead and draw that chair conformation, and we will draw an equilibrium arrow, and there we go. There's our other chair. That is the exact same chair. Nice. You guys get to watch me struggle too. Why not? Actually, it's not fair. I don't get to see you struggle, but I don't really want to see you struggle. I want to see you guys kill it. All right, so let's take a look. What we have is, let's do these ones in red. This one I will do cis. So you know how I roll. I want to make this is the 1, 2, 3 position. That means Jess wants to put it in the axial position. And then at the 3 position, since it is a methyl and it is cis on the same side, this is an up methyl. That means we need an up methyl over here. And there you go. Once you do that ring flip, so that's 1, 2, 3, that means we have to have an up methyl here and an up methyl here. Okay, so which one is more stable? Yeah, you guessed it, more stable. And again, that's because we have the substituents in the equatorial position, as opposed to that 1,3 creating that in the axial position, which creates that 1,3 diaxial strain. All right, so let's take a look at the trans isomer. So boom, boom, and let's see. I gotta think about this one again. And there we go. And let's go red. Let's go blue, just cause. All right, y'all. Where do I want to put my methyl? I want to put the 1 methyl in the axial position, and then the other methyl on the trans isomer, which is what we're doing, has to be opposite. So if this is up, then the other methyl needs to be down. And so since this is an up C, the down position is actually equatorial. Okay, so that is just going to be sticking out like that. All right, so let's do a chair flip and see what happens. This is the 1 position, then the 2, and then the 3. And since it was an up methyl, we want to place that there. And the 3 position, it was supposed to be down, so that means we're placing it down there as well. So the which one's more stable? Remember up here we kind of had the same stability when we had one in the axial, one in the equatorial, one in the axial, one in the equatorial. So they have the same stability. So here's the thing. This is the trans, right? So the trans isomer in this case has the same stability for this particular disubstituted cyclohexane. But if you look up here, that one that had the same stability above was the Cis Isomer. So what does that mean? That means that we can't generalize basically which one is more stable based off of being cis or trans. It actually depends on where the substituents are. So is it a 1,2 disubstituted, a 1,3 disubstituted, or a 1,4 disubstituted? And then that's basically the reason for drawing these 2 different structures. It's really important for you to be aware of it, be able to draw them all out, so that way you can figure it out, and then you'll be cyclohexane chair champions. All right, you want to talk about practice? Let's talk about practice. Okay. Let's see. So, how about this? Give you that one time. Give you that one time. Let's see. There's that chair structure. There's that one. I'll explicitly draw the hydrogens just so you know the direction of the chlorine. Basically, is it cis or trans? Cis or trans? So, one way to tell is basically look for the axial position. I like to look at the axial position. If the axial hydrogens are on the same side, then that means that so are the OHs, right? So that means this must be cis. So for this one, since this axial hydrogen is up and this one is down, that means these two chlorines are opposite, so that means they must be trans, okay? So that's just kind of how I personally do assess whether or not things are cis or trans. You could also just look at both of the OHs or both the chlorines and determine if they're up or down, okay? So I feel like it's less thinking though if you just focus on the axial hydrogens, okay? So let's see, let's try another one. Draw the chair conformation for conformation with one methyl group and then one CH3CH2 group. So one methyl group and then one ethyl group. Okay, so this would be a CH3, CH3, CH2. Okay, so remember we can abbreviate those. But let's see, let's say we had a cis, a 1,2 disubstituted cycloalkane with the CH3 in the axial position. Okay, so that means that we need to figure out where the ethyl group goes. So let's go ahead and draw our chair. Oh my goodness, what are you even doing, iPad? All right, so now that we've got that going, we want to draw our methyl group in the axial position just to make it so that you can observe more types of substitution. I won't do it here, even though that's where I want to very badly. Let's just do it here. So if that methyl group has to be in the axial position, this is a down C, so that means that methyl group needs to be down, okay, in the axial position. And so if we want our compound to be cis, that means we want our ethyl group to be down as well. If this is a 1 position or a 2 position, then that would be the 1 or 2 position as well. So they're basically the 1, 2 means they need to be right next to each other. Technically, I could put it here or here because that would be a 1,2 disubstituted substituent, or I'm sorry, a 1,2 disubstituted cyclohexane, but I will put it on this one just again so that you can see how things look in a different orientation. It's not always going to be pretty and just substituted right here. So we need to put that ethyl down, remember? So if you look at this point, this is an up C. That means the axial hydrogen would be up and the ethyl would be down. So I forgot I didn't do the ME over here for you, but this would be an example of the cis 1,2 disubstituted with the methyl group axial and then the ethyl group cis and then equatorial down. Okay, let's look at one example of a trans substituted one. So let's say it's trans and it's a 1,3 disubstituted. Holy moly. Disubstituted, and it's got a methyl group in the equatorial position. Okay, let's draw it. First, draw your chair, and we've got our, let's see, tell me when to stop. Do we want it here, 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 here? All right, I didn't hear anybody, so I'll put it wherever I want. All right, so let's put it here. That's terrible. Boom. Let's put a methyl group there, which is an Me. And if we want it in the 1,3 position, that means we need to skip a carbon and then put our ethyl somewhere else. So that means our ethyl could technically go here or here. So let's put it, where do I want to put it? I'll put it here. All right, so the trans means that if this methyl group is down, that means our ethyl group needs to be up. And so at this particular carbon, if it's up, it's an up C. That means the up position is an is an axial position, and therefore our ethyl group looks like that. All right, cool. So that's gonna pretty much be it for the cyclohexane mono and disubstituted and the chair conformations for you. So let me know if you have any questions, and have fun with these, and make sure you get a lot of practice.